Hi everyone. Today I want to talk a little bit about power sets, which is a topic that we'll be discussing in class for the next few days. And so I know that we've already seen the definition of a power set on the last homework assignment, but I want to review it quickly here. And so a power set P of a set A is just the set of all subsets of my original set. That's certainly a mouthful, but hopefully it's clear as soon as we look at an example. So here if we have A being the set 1, 2, 3, then the power set of A is just the long laundry list of all of the subsets in this set. And so that is easiest to write if I keep organized, and I'm going to write the sets in smallest to largest order. And so the smallest subset of any set is always going to be the empty set. And then I'll write all the sets of size 1, which would just be 1, 2, and 3. And then I can write all the sets of size 2, and so that would be 1, 2, 1, 3, and 2, 3. And then there's only the one set of size 3, which is the original set back. And so in this case, we can see that there are 8 subsets of this original set A, and that is 2 to the third, which is a more general phenomenon. And so if a set A has n elements, it turns out that the power set has 2 to the n elements. And that's because you can decide whether or not to include each element of A in the subset. And so we have 2 choices for each element in A, and we get 2 times 2 times 2 times 2 up through n different times, and so that gives me the 2 to the n. Okay, so as we've seen throughout this course, a lot of the time we're going to want to make conversions of different notation whenever we see something in a proof. And so now that we're talking about power sets, we're often going to see the expression that X is an element of a power set. And in this case, that is an indication that we're probably going to want to change to saying that X is a subset of A. And so that's pretty obvious given the definition of a power set, but that is a common conversion that we'll want to make. And so to see that conversion in play, we're going to look at this relatively simple example right here. And so the question is, if we know that the power set of A is equal to the power set of B, does that mean that the original sets had to be equal to each other? And so if I say this verbally, we just know that 2 sets have the property that all of their subsets are equal. And so it is the case that that does imply that the sets themselves must be equal. And so this statement is true. And so if we want to prove this statement, it'll have the typical overall structure of a proof of this form for set equality, which is that we'd want to show subset relations in both ways. And so here we're going to start the proof by assuming that the power set of A is equal to the power set of B. And now I'll want to show that A is a subset of B. And then I'll show the other direction after that. And so here I'll just let X be any element of A, and now I want to show that it's an element of B. And the way I'm going to do it is by shifting everything so that it's talking about subsets. And so if X is an element of A, then of course I know that the set that contains X is a subset of A. And so if that's true, that means that the set that's containing X is an element of the power set of A. But we already know, we're assuming, that the power set of A is equal to the power set of B. And so that implies that this set X is a subset of B, and in turn that implies that X must be in B. And so we've finished this side of the proof right here, and the proof that B is a subset of A is the same, just with A and B swapped everywhere. And so there's no need to write out all of those details again. But again, the important part of this proof right here was this conversion from X being in A to a statement about subsets so that we could use the facts about the power set. All right, let's look at one more example here, and this will just help us see more about the structure of power sets. And so here I want to know how many elements of this power set have size 2. And so that's just phrasing for saying how many subsets of the set have 2 elements. And so in order to answer this question, one option, which is true for a lot of counting problems, is to try and come up with an algorithm that could produce subsets of size 2 and then count how many ways there are to use your algorithm. And so here we could have our algorithm be pick the first number in the subset, and then we could pick the second number. And so that seems like a stupid algorithm, but we will be able to count everything along the way. And so if we're picking one of the numbers in this set to be in our subset, there are 5 choices, because we could pick 1, 2, 3, 4, or 5. And now that we've picked one number, to pick the second number, there's only 4 choices. And so there's a tiny issue with this algorithm so far, which is that if I consider, for example, the subset 1, 3, then there's 2 ways that I could get it with this algorithm, because I could either pick the 1, then pick the 3, or I could pick the 3, then pick the 1. And so I now have to divide by 2 for overcounting. And so at the end of the day, that tells me that the number of subsets of size 2 is going to be 5 times 4 over 2, which is equal to 10. Or you might remember from previous math classes that this could also be expressed as 5 choose 2, which is just the notation for saying that you have 5 elements and you're going to pick 2 of them.